അതല്ലേ അങ്ങനെ ഒന്നും ഉപയോഗിക്കാനില്ല. എന്തെങ്കിലും ആവശ്യമുണ്ടെങ്കിൽ ഉപയോഗിക്കാൻ അതിലൊന്നും ഓപ്പൺ കഴിയില്ല. ഞാൻ നമുക്ക് വാട്സപ്പിലായിട്ട് എടുത്തിട്ട് അത്രേ പറ്റുമോ? ഞാൻ എന്തെങ്കിലും സിമ്പിൾ എന്തെങ്കിലും ആവശ്യമുണ്ടെങ്കിൽ ഉപയോഗിക്കാൻ വെച്ചെടുത്താ. ആക്കിക്കോ. നോക്കണം. ഉടായ്പ പരിപാടിയാണ്. ആ ലൈവല്ല, ജസ്റ്റ് ഇവിടെ കൊടുക്കാൻ. എന്ത് കൊടുക്കുന്നേ? അതില് വേറെ വേറെ ചെയ്തോ. ഞാൻ വെറുതെ ഇവിടെ സ്ക്രീനിൽ കൊടുക്കാം. അപ്പൊ നമ്മൾ ലിങ്കില്ല. ഓഡിയൻസ് അങ്ങോട്ട് കാണണം. ഓക്കെ, ഞാൻ ഒരു കാര്യം ചെയ്യാം. ബുഹാരി വരാൻ വേണ്ടി മണിയാകുമ്പോ മാറാത്തൊന്നുണ്ടാ? ഇവിടെ കൊടുത്ത് ഏത് എന്താന്ന് പറ. അവിടെ പരിപാടി എടുക്കുന്നത് റൂമിലേക്ക് കൊടുക്കണം. സെറ്റ് എടുത്തിട്ട് കൊടുക്കും. തന്നാലും കൊടുക്കാലോ. ഏത് ഡ്രൈവ്? ജിമെയിലാ? വിസ്ഡം വിസ്ഡം ഡോട്ടൊന്നുമില്ലല്ലോ. ഡോട്ടൊന്നുമില്ലല്ലോ. ജോബ്സ് 2022 ജിമെയിൽ. ജോബ്സ് 2020. ലേഡീസിന് വരുന്നുണ്ടല്ലോ പ്രശ്നമാണ്. ലേഡീസ് വരുന്ന പ്രശ്നം ഇതാ. ഏതാ? പറ്റില്ല. യൂട്യൂബ് ആണെന്നല്ല, ഇവിടെ പോയിട്ട് തുറന്നാൽ മതി. യൂട്യൂബ് ആ ഞാൻ എങ്ങനെ കൊടുക്കുന്നത്? അവിടെ പോയിട്ട് തുറക്കാൻ മതി. ഇവിടെ എന്താ കൊടുക്കുന്നത്? എല്ലായിടത്തും എന്താ കൊടുക്കേണ്ടത് എന്നോട് പറഞ്ഞു. വെച്ചാല് വേണമെങ്കിൽ ഒരു കാര്യം എവിടാണ്? പിന്നെ എന്താ സംബന്ധം? ആ ആ അത് ഇങ്ങനെ ചെയ്താൽ മതി. എന്നാ എന്താണെന്നറിയാം. ആ ലൈവായിട്ട് പോകുന്നില്ല, ആ ടീം
how to calibrate them, and how to use them with microcontrollers. We'll also build a soil moisture meter and an automated watering system that you can control with the Arduino IoT Cloud. We're growing something special today, so welcome to the workshop. Well, hello and welcome to the workshop, and today we're working with soil moisture sensors, which you can probably guess from their name are devices that you place into the ground and they'll measure the amount of water content in the soil. Now we're going to learn about how these sensors work, we're going to calibrate a few of them, and then we're going to build a couple of projects. The first project is a soil moisture meter with an Oled display, and our second project is an automated watering system that's going to be using the Arduino Arduino IoT cloud so that we can water and maintain our gardens from pretty well anywhere in the world. Now, before we go on with our lessons and our projects, there is a bit of a disclaimer I have to give. Now, there are some people out there, perhaps you're one of them, who are just wonderful with gardening. They can grow beautiful crops of vegetables, they can make gorgeous flowers, they're just whizzes in the gardening. We call these people with a green thumb. Well, if you look on the color wheel, the opposite of green is red, and so I probably have a red thumb because plants do not do well with me. I've never been good at gardening. I've even managed to kill plastic plants. So I'm not the kind of person who can dispense advice about gardening to you. I can, however, dispense advice about technology. So let me dispense some right now by telling you how soil moisture sensors work. Soil and moisture sensors have applications in agriculture, irrigation, research, and just plain gardening. Some advanced soil moisture sensors use the property of water to alter microwaves, and they use techniques such as frequency domain reflectometry and time domain reflectometry. A very advanced method of measuring soil moisture is neutron scattering, which uses the moderator properties of water on neutrons between a source and a sensor. The soil itself can also act as a galvanic cell. This allows the construction of a soil moisture detector that does not require its own power source. The resistance and capacitance properties of soil can also be used to measure soil moisture. Today we'll be focusing on inexpensive sensors designed for microcontrollers and microcomputers. These sensors are based on either the resistance or capacitive properties of the soil. These sensors can be run in multiple modes. In analog mode, the resistance or voltage output will change in response to the amount of moisture in the soil. In digital mode, a set point is established and the output will go either high or low depending on whether the moisture is above or below that set point. In addition to analog outputs, there are also serial and I2C devices available, and we'll be taking a look at an I2C device later on. A common application for soil moisture sensors is an automated watering system, and we'll be putting one of these together later on in the video. In this sort of system, a soil moisture sensor is connected to the input of a microcontroller. It's also typical to have some sort of a readout of soil moisture as well. You will also connect a pump or other source of water to the output of the microcontroller. If the sensor detects the moisture dropping below a certain point, it will activate the watering system and water the soil. Once the moisture has gone above a certain threshold, the watering will stop. Resistive soil moisture sensors depend upon the resistance property of soil, which decreases with the amount of moisture in it. These are very simple to design and quite easy to manufacture. However, they have one major drawback in that corrosion of the probes can alter its resistive properties. With a capacitive soil moisture sensor, the soil itself serves as the dielectric within a capacitor. These sensors have a timer on them that measure the amount of time that this capacitor takes to discharge. Because we're measuring soil capacitance, we don't require any direct contact to an electrode, so the electrode can be insulated, and this eliminates the corrosion effect that occurs with resistive sensors. Resistive sensors have an advantage in that they are a lower cost. Capacitive sensors, however, are longer lasting and generally provide better performance. As these sensors both provide analog outputs, they can both be used in our designs, so you can use any sensor you happen to have with the circuits you're about to see. So now let's take a look at a few soil moisture sensors. Now here are some soil moisture sensors for you to take a look at. We're going to be using a few of these later on in some experiments. 3 of these are capacitive sensors and one of them is resistive, and you can sort of tell which one the resistive one is. It's this one here, and it has these 2 electrodes, and what we're actually doing is measuring the resistance between the electrodes. So when that's inserted in soil, the soil will provide an electrical resistance, and that's what's being measured in these. The rest of these are capacitive sensors, so you don't actually see any electrodes. They've all been nicely sealed up and protected from the elements, so there's nothing going to corrode because, of course, a capacitive sensor works on a different principle. In this case, the soil becomes a dielectric in the capacitor. Now, this is a very standard and very common capacitive soil moisture sensor, and these ones are quite inexpensive, and it has an analog output. These other two have I2C outputs. This one is made by a company called Catnip Electronics, and it's a very interesting little sensor. It also measures temperature and light. One other thing about it, though, is it didn't have a connector on it, so I had to solder these jumper wires onto the output here, but this has an I2C output, so I've got power, ground, SDA, and SCL coming out of here. This is also another I2C sensor, and this one is called a Seesaw, and it's made by Adafruit. It does have a little connector on it, so it's a little bit easier to use, and these other ones also have connectors as well. But there you go, a few soil moisture sensors that we can be using in our experiments. Now, before we put our soil moisture sensors to use, we need to calibrate them. It doesn't matter whether they're resistive or capacitive. Each sensor has its own unique properties, and even if you get a batch of them, you'll find that no two of them are exactly alike. Now, calibrating the sensor is pretty easy. All you need to do is take a measurement of its output when it's completely dry, and then take its output measurement when it's completely wet. And since resistive and capacitive sensors both output a voltage in response to the amount of soil moisture, we can use the same circuit and the same sketch to calibrate both of them. Now, I'm going to be doing this with a Raspberry Pi Pico. It's an inexpensive microcontroller, and one of its advantages is that it has a 12-bit analog to digital converter, so we can get a very accurate reading from it. Now, I'm also going to be using the classic Arduino IDE 1.8 for these experiments, and if you haven't used the Pico yet with the Arduino IDE 1.8, I urge you to go and take a look at that monster-sized video that I just did for the 10th anniversary of the Raspberry Pi. You don't have to watch the whole video, but go to the third project. You can use the table of contents in the video to go there directly, or use the chapters feature on the YouTube video. The third project was a Raspberry Pi Pico Simon game, and I show you exactly how you set up the Arduino IDE to use the Pico, so I'm going to assume you already know how to do that. Now, if you don't want to use a Pico, I'm also going to show you how you can use these calibration with a Arduino Uno, and it's basically the same sketch with one modification, and I'll show you the hookup for the Uno as well, so you don't necessarily have to use a Pico, although you will get more resolution. So let's go and take a look at how we hook up the Pico, and then I'll show you the sketch that we're going to be using to calibrate both our resistive and capacitive soil moisture sensors. For our experiments, we're going to be using a Raspberry Pi Pico microcontroller. However, you could use a different microcontroller, and I'll show you how to do the same experiments with an Arduino Uno a little bit later. We will also, of course, need a soil moisture sensor. You could use a resistive sensor or a capacitive sensor because the hookup and the code are identical for both. I'll be using a capacitive sensor in this illustration, but again, the hookup for the resistive sensor is identical. We'll start by connecting the analog ground pin of the Raspberry Pi Pico to the ground of the soil sensor. You could also use another ground pin if you wish, but analog ground is the specific reference for the analog to digital converter and will produce the best results. We use the Pico's 3.3 volt output and connect it to the VCC of the soil moisture sensor. And analog to digital converter 0 input, which is also GP26, will be connected to the output of the soil moisture sensor. And this completes our wiring. Now let's take a look at some code we can use to calibrate our sensor. Now here's the sketch that we're going to be using to calibrate our sensors, and we can use this with both capacitive and resistive sensors, and it's an extremely simple sketch. We start off by defining a value that we're going to be using to get the sensor value, and this will be the output of the analog to digital converter, and then we define the analog to digital converter pin itself, which is ADC0. Then we'll open up our serial monitor so we can see our results, and we're also going to set our analog to digital digital converter resolution to 12 bits. If we don't do this, it'll default to being 10 bits, and we want to get all the resolution we can. And then in the loop, it's extremely simple. All we do is we use an analog read to read the value from the sensor pin and assign it to sensor val, and then we just print that to the serial monitor. We add a very short delay, and we continue to do that. And so a super simple sketch. Let's try it out with both capacitive and resistive sensors. So we're going to start off by calibrating the capacitive sensor, which I've got hooked up to the Pico right now, and as you can see in the serial monitor, I'm getting a reading, and it's hovering around 2500, 2523, 2518. This will be my dry reading, and I want to record that because this is what I'm getting at what should be about 0% moisture. Now I'm going to stick it into this glass of water, and you'll see that the reading went down. It's going down about 1340, 1350. This will be the reading that I'm going to get from my wet reading, and so you'll also want to calibrate that. So those are the two different extremes of the sensor, and we'll be using those calibration values in further experiments. Okay, now we're working with the resistive sensor, and the first thing you'll notice on the serial monitor is that the dry reading is a very, very low value. It's down around 20. It even approaches 0 at times. And when I put it into the water, you'll notice that the wet reading is very high, and there's quite a discrepancy between the two. And with that kind of a range, it means that this type of soil moisture sensor is actually more sensitive to small differences in soil moisture. So in some ways, it's a bit more accurate. However, of course, the resistive ones do have a problem in which the probes will eventually start to corrode, and the values will start changing. They'll go out of calibration. But as you can see, we can use the same circuit to calibrate both resistive and capacitive soil moisture sensors. Now you could also use an Arduino Uno to perform these experiments. Again, I'm showing a capacitive soil sensor, but you could use a resistive sensor as well, as the hookup is identical. We'll start by hooking the ground of the soil sensor to the Arduino's ground. The VCC of the soil moisture sensor will be connected to the 3.3 volt output of the Arduino Uno. The output of the moisture sensor will be connected to analog pin A0. And you'll also want to connect the AREF, or analog reference pin, on the Arduino Uno to the 3.3 volt output. Now let me show you the changes you need to make in the code in order to use an Arduino Uno.
Aerial pod with 2 times more cleaning power versus gel for better stain removal.
Now there's only one change you're going to need to make in the code to run this with an Arduino Uno, and it's down here in the setup. This command analog read resolution is not going to compile with an Arduino Uno because the Arduino Uno only has a 10-bit analog to digital converter. At the same time, if you remember in our wiring, we've wired the AREF, or analog reference pin, to 3.3 volts, so we need to use that. So change analog read resolution to analog reference and make this value here external, like this. And that way you'll use the 3.3 volt power supply that we fed into the AREF pin, and you also won't have an analog read resolution that was set there, so obviously this line is incorrect right now. But that's the only change you need to make, and you can run the code on an Arduino Uno. Now, when I showed you all of the different soil moisture sensors that I've collected, I showed you 2 models that were using an I2C interface. Now, these are capacitive soil moisture sensors, and so they work in a similar fashion to the capacitive sensor we've already worked with, but of course their output is different. They are I2C, and therefore they can be used with just about any microcontroller or microcomputer that supports I2C. I2C. Now, one of the models I showed you was from a company called Catnip Electronics, and it's a very interesting sensor. Not only does it give you soil moisture readings, it also outputs temperature and light level readings, and it's quite easy to use as long as you use a library with it. So we're going to take an Arduino Uno and my Catnip Electronics I2C sensor and see how we put them to use. For our I2C experiment, we'll be using an Arduino Uno. We'll also require a Catnip Electronics I2C moisture sensor, and you'll need to solder some wire onto the connections in order to make use of it. We'll begin by connecting the ground connection on the moisture sensor to one of the grounds on the Arduino. We'll connect the moisture sensor's SDA output to analog pin A4 on the Arduino. We'll connect the SCL input to analog pin A5. And the VCC pin on the Catnip Electronics I2C moisture sensor will be connected to the Arduino's 5-volt output. And this completes our wiring. Now let's take a look at some code we can use with the moisture sensor. Now the I2C soil moisture sensor that we're going to be using is a great example of some of the electronics that we're seeing from all over the world. This was built by a company called Catnip Electronics, and they're in Lithuania. Now you can get this off of Tindy where they sell it directly, and as you can see it's not particularly expensive, but I actually got mine from Mouser Electronics, and so you have that as an option as well. Now wherever you happen to get it from, you're going to need a library in order to use it properly, and there are a lot of great examples up on GitHub for doing that. There are also Python examples up on GitHub, so you could use it with Python or MicroPython, use it with a different microcontroller, or perhaps with a Raspberry Pi, but we're going to be using it with an Arduino Uno, so we're going to get some Arduino code, and here's where you can grab a library on GitHub. You just hit code and do download zip, and you'll get the library in a zip format. Now you'll need to install that into your Arduino IDE, which I've just done, but I'll show you how you do it. You just go under Sketch, you go Include Library, and then from Include Library you do Add Zip Library. You navigate to where you're downloading your files, and here it is, the I2C soil moisture sensor. You would hit OK, but I've already done that. And now you've installed the library, there's also an example sketch that we can use in order to work with it. So just go into File, go into Examples, go down to Examples from Custom Libraries, and you'll see I2C soil moisture sensor. And you've got two of them, one that allows you to change the I2C address on the device, the other one called reads.
Knowtech in the logo is it inside. അതിങ്ങനെ വെച്ചിട്ട് ആ ബാക്കി ഭാഗം നമുക്ക് യൂട്യൂബ് അപ്പൊ നമ്മളൊരു ഇതിൽ ഓപ്പൺ ആക്കാനാ ഇതിന്റെ അല്ലേ
185. So once again, this is a useful soil moisture sensor, and because it's an I2C device, you can use this with microcontrollers and microcomputers that don't happen to have an analog input. So now that we've seen how soil moisture sensors work and we've calibrated a few of our own sensors, it's time to put them to use. And the first project we're going to build is a soil moisture meter. Now this meter has an OLED display that will display the percentage of moisture in the soil, and it's based around the Raspberry Pi Pico. Now you're going to need the calibration values you took for your soil moisture sensor in order to complete this job. So if you haven't done that yet, go back and calibrate your sensor first. And after you've done that, let me show you how you wire up the soil moisture meter. We'll be constructing our soil moisture meter with a Raspberry Pi Pico. We'll also be using an OLED display, a standard SSD 1306 display with an I2C input. And of course, we'll require a soil moisture sensor. Again, you could use a resistive or a capacitive sensor, and I'm illustrating a capacitive sensor here. The connection for the soil moisture sensor is identical to the ones we used for calibration. We'll start off by connecting the ground of the soil moisture sensor to the analog ground or AGND pin on the Raspberry Pi Pico. The VCC connection on the moisture sensor will go to the Pico's 3.3 volt output. And the output of the soil moisture sensor will go to analog to digital converter 0 input on the Raspberry Pi Pico. This is also GP26. We'll connect the ground of our OLED display to any of the grounds on the Raspberry Pi Pico. You can identify the ground pins on the Pico as they have square pads. We'll connect the VCC of the OLED display to the 3.3 volt output of the Raspberry Pi Pico. The SCL or clock pin on the OLED display will be connected to Pico pin GP5, and the SDA or data pin on the OLED display will be connected to Pico pin GP4. And this completes our wiring. Now here's a sketch that we're going to be using for our soil moisture meter, and it's been written to use capacitive sensors. However, you could rewrite it for resistive sensors with one simple change, which I'll show you in a moment. Now we start off by including some libraries that we're going to need to drive our OLED display. We need the wire library because that's the library for I2C, and that's already included in your Arduino IDE. The next couple of libraries are libraries from Adafruit, and if you don't have them, go into your library manager and look for SSD 1306. Install the Adafruit library, and it'll also install this other library for you. However, if you've already played with OLED displays, there's a good chance you have these libraries already. Now we're going to go and set some parameters for the OLED display. So we set its height and its width, and we set some other parameters up as well. This reset as -1 just needs to be set so we know that we're not using a separate line for reset. And the screen address, and this is the I2C address. Now, if you happen to have a display that has been set to a different I2C address, you will of course need to change that. Then we define an object called display by passing it all of the different parameters for the OLED. And then we go and we put in our sensor constants. Now these are the values that we determined from the calibration sketch that we ran earlier. So your values could very well be different than mine. You could start off with these and experiment with them, but the best way to do it is just to calibrate your sensor using the sketch that we looked at previously, and then plug the values in over here. We set up a couple of variables we're going to need for the soil moisture. We're going to get the soil moisture value, which is actually the value that we get from the analog to digital converter output, and we're also going to get the value in percentage, which is what we want to display on our display. And then we define the port that we're using, which again is ADC0 for the input from the sensor. In our setup, we're going to set up the serial monitor, and we're just using the serial monitor for troubleshooting, and also so we can fine-tune those wet values and dry values up over here. We might want to change them, and the serial monitor will help us do that. We're going to initialize our display, and an important thing when we initialize it is this switch cap VCC parameter that we use when we initialize it. If we don't use it, if we just use SSD1306, it's going to expect the 5-volt power supply, but in this case it'll know it's getting a 3.3-volt power supply, so you need to plug that in, and then the screen address itself. Then we're going to clear our display, and once again we'll set the analog to digital converter to use 12 bits with an analog read resolution function. Then we go into the loop, and in the loop, just as we did with the calibration sketch, we're going to get the value from the sensor, assign that to the soil moisture value, and we'll print it out to the serial monitor, and then we'll go and we're going to determine the percentage, and we do that with a map command, and we take the soil moisture value and we map it between the dry value and the wet value to a value of 0 to 100 to get the percentage. Now, I said earlier that you would possibly be able to use this with a resistive sensor, and you can. What you need.
Hello everyone, this is Neil from Edureka and welcome to this IoT tutorial session. Now, IoT, or Internet of Things as it's most popularly known, is one of the greatest phenomena of this century. It's gained a lot of popularity, and in today's session we'll be getting a brief idea of what IoT is, and we'll also be working on a demo using Raspberry Pi. Now, going on to the agenda for this session, we'll start off by first understanding what is Internet of Things, and then we'll try to address the question, why do we need Internet of Things? Going on from there, we'll talk about the various benefits of IoT as well as the various features of IoT as well. And finally, we'll be moving on to the demo of this session, which is basically creating a weather station using Raspberry Pi. We'll mainly be measuring three things. We'll be checking the temperature of the environment, the pressure, as well as the humidity present. Okay, so these are the three things that we'll be measuring using Raspberry Pi and another component known as sensor. Okay, so moving forward, let's talk about the first topic of this session, which is what is Internet of Things. Now, to help you understand what is Internet of Things, let's look at an example of our mobile phones first. Okay, our mobile phones has GPS tracking, it also has mobile gyroscope, you have adaptive brightness which gets adjusted based on the light falling on it, you have voice recognition, and you also have face detection which identifies who is the user. Now again, iPhone X is coming with face detection, so again these are a lot of features that are coming pre-built on the mobile as such. And most of these have a common interaction between them, because let's say one application can use all of these features. I can also have these features in itself being interacting with each other. Let's say based on a GPS location, my brightness could be adjusted, or based on the direction my phone is being held, the brightness in itself can also be adjusted as well. So there are a lot of features, but when they interact with each other, these features come together to bring in a better system than anything that they can provide individually as such. That's what Internet of Things is. It basically is a platform wherein we can connect everyday things which are embedded with either electronics, software or sensors to the internet, and this in turn enables us to collect as well as exchange between these things. Now, when I say things, it can be anything and everything. Let's say I have an internet platform wherein I can connect these things. If I take the example of my house, I can connect my lock, I can connect my AC, I can connect my lights, and all this can be managed on the same platform. Now, since I have a platform itself, I can also connect my car to this. I can keep a track of my fuel meter, I can keep a track of my speed limit, I can also keep track of the location of the car as well. Now, if there's a collective platform where all of these are connected, wouldn't it be great? Because I would love to have the AC on and set a cool temperature at my home by the time I reach back from office. If I have a platform that knows my preference and that keeps track of where I am and where I'm going to, then it can also identify that I'm going from work back to home, and my preference suggests that it would be best if there was an AC temperature of about 22 or 23 degrees centigrade. And this is something that is definitely possible through Internet of Things. And this is just one of the examples. Now, let's say tomorrow you come back home. It would be great if I wouldn't even need a key to unlock my door. My home system should be aware that I have come home and it should unlock all the doors that are needed. And now this can be done if my mobile and my home devices are connected onto the same platform. Based on the location of my mobile, it can identify that I am at my home. So it will automatically unlock the door and let me come in as well. These are some of the real world implications of Internet of Things. These are something that are already happening. But going forward, what we need to understand is that when I have a specific component with me which can do a lot individually, wouldn't it be great if I can collaborate this component with my system of different components and build a better system? This is what Internet of Things is helping us do. Okay, you provide a platform through which all these things are connected through the internet. So internet becomes the medium through which you're connecting all these components or things to a platform. Okay, moving forward, let's try to understand why do we need Internet of Things. Now to help you understand why, let's look at an example. There's a patient at home. Okay, he's on constant life support wherein his status is being checked to a health monitoring system present on the cloud. Let's say at a point there is certain issue with respect to his health. Let's say there's some irregularity with his heartbeat or his blood pressure is low, there's some fluid being developed or so forth. Now what happens is, since the system on the cloud is connected to a hospital as well, this information would get passed on to the hospital as well. Therein what would happen is that they would get the complete details with respect to the patient and the important information with respect to the current situation of the patient as well. We made it aware with respect to what issue exactly is the patient facing, as well as enable them to dispatch an ambulance immediately to bring the patient back to the hospital as well. Now, meanwhile, once the patient has been picked up and brought back to the hospital, there could be prescriptions, there could be medicine, there could also be an operating theater made ready in case of an emergency situation as well. There'd be doctors on standby who have the complete history of the patient, who have the complete details of the present condition of the patient as well. So this in turn brings in a lot of transparency and reduces a lot of effort and time involved with respect to this. Same thing, let's take in today's scenario, there has to be someone monitoring this patient's health. And if there's a fluctuation, they need to call the hospital, they need to call request for an ambulance. And meanwhile, once the ambulance is here, they take the patient and they're back into the hospital. Then again, there needs to be a lot of checkups that need to be done because the doctors are not fully aware. Again, there is a lot of tests that need to be run, and this in turn leads a lot of delay as well in certain emergency cases as such. Now, if a system can do this, then this is exactly where our future lies in and what we have to definitely move forward to. Now, Internet of Things basically is expanding the interdependence of humans to interact, contribute, and collaborate with things around us. Now, what do I mean by interdependence of humans? How we depend on each other. Like how I'm explaining this concept to you. If you're not clear, you would reach back to me, you would request me for help. Okay, this becomes an interdependence between us, where I'm giving you knowledge. When you're not clear, you're coming back to me and you're helping. Similarly, tomorrow, if there's something that you can do for me, I would reach out to you. So we all are interdependent on each other for something or the other. If we can expand this interdependence to interact, collaborate, and contribute with respect to the different things around us, then we would be building a proper Internet of Things environment. This would be a much more safer, secure, effortless, and time-saving environment in existence. Moving forward, let's talk about the various benefits of Internet of Things. Now, the first thing that would be as a benefit of having an Internet of Things platform would that we could efficiently utilize the resources that are available. If I have a smart system which can interact with everything, if it has enough computational power, if it has enough understanding of how things work between each other, I'm quite sure the usage of the resources available will be more efficient as well. This resource could be in terms of monetary, it could be in terms of natural resource, it could also be an input taken up by the team as an input and so forth. Okay, so all this can be more efficient if I have a platform which is more smarter and interconnected as well. Apart from this, it minimizes the human effort involved. If my system is smart enough to interact, if it is smart enough to do things that I don't need to get involved with, then my interaction is always going to be minimal. This is the same with everyone. And that's one of the major reasons why Internet of Things has become popular today, and the concept of smart home is always growing as well in the same perspective. Because if the system in itself is able to do most of my work at home, then I don't need to put in much effort. I can relax at home without having to worry about anything. Okay, the next benefit would be it saves time. If it reduces my human effort, definitely it is going to save my time. Okay, apart from that, if the resources are utilized more efficiently, then again it is going to save a lot more time as well. All in all, any benefit of Internet of Things will in turn help you save a lot of time as well. Okay, so time is one of the major factor that can be saved on an Internet of Things platform. Now, if I have an artificial intelligence platform through which all of this is managed and maintained, then the personalization and the human touch also comes into the picture. Now, today most of us have had a level of interaction with an artificial intelligence or a virtual intelligence as well. This could be a personal assistant like Siri, or it could be an assistance application like Google Assist. Now, if I have a system where all these components and things are interconnected, then in turn all the security present on each of these things is going to get multiplied and it's going to build a much more secure system. Apart from that, the level of security that you would be integrating to the platform in itself is going to be quite huge. So the overall security with respect to everything is going to increase multiple times as well. Now let's look at some of the major features of Internet of Things. Now, any technology that is available today has not reached its 100% capabilities, and it always has that gap to grow. Internet of Things is one of the major technologies in the world today that can help any other technology reach its
Hello?
true and complete potential as well.
Ah.
Now, there are mainly three aspects to Internet of Things as to how it works. First
Live
is the
from
connect aspect. Here, basically what you need to work on is you need to ensure that there's a connectivity between all the things around you, all the necessary things to the Internet of Things platform. Okay, then comes analyze. Now I have my things around me, they each are going to generate some amount of data. Now this data needs to be collected and it needs to be analyzed to build a business intelligence solution. If I have a good insight from the data that is gathered from all of this, then definitely I can call my system as a smart system. Finally, what happens is, in order to improvise and improve your system, you need to integrate it with various models to improve the user's experience as well. Let's say there's a personalization module that is there, or let's say there's going to be an aspect wherein I can directly connect to my providers. Now this provider could be Amazon, it could be Flipkart, it could also be my retail store that is next to me. Let's say I'm out of milk, the retail store would get a notification and he would send milk right away. And the same thing can be done. Let's say my coffee machine requires special beans and this beans is almost complete. Then what my system could do is it could go online to Amazon and purchase these beans for me as well. So there are a lot of things that I can do when I integrate this with respect to various models and improve the overall experience to a single user or a group of users or the world itself as such. Okay, now let's talk about each one of them one by one. Let's start with Connect. Now, the first stage of Connect is device virtualization, because what you need to first do is that you need to standardize the integration of the device to the enterprise platform which is present on the cloud. Okay, now it could be present on a cloud, it could be present on a server, but again it's all going to be connected through the internet. So what I need to do is that I need to ensure that certain level of standard is present on the device so that it can go on and connect to my Internet of Things platform. Now, to help you understand this better, there could be a standard power plug and there could be a power plug which has an inbuilt Wi-Fi support so that it can connect to my LAN. Now, to build a smart home system, I need the second power point because there only I would have the access to control it over the internet and my system could integrate with respect to the same. Okay, now if I take the first standard power point, then what would happen is that I need to manually switch it on and switch it off. However, in the second case, I could send a signal to it and this in turn will switch it on and switch it off. So there's supposed to be a level of standardization through which I can integrate all of these devices to my platform. Next comes high-speed messaging. So now what I have done is that I have connected all these devices to my platform. But these devices in turn generate a lot of data, and this data is what is going to help us understand better on how we can improve the overall system and help and provide the user with better experience. So for that we need to have high-speed messaging. Okay, this basically means that there needs to be a reliable, secure and a bidirectional communication channel between the devices and the platform. Now the purpose of it being bidirectional is because you need to control each one of them as well. Let's say I want to switch on the AC, then the signal would be going on from the cloud platform to the device. So this is how it works on. Okay, so every communication needs to be reliable, it needs to be secure, and it needs to be bidirectional as well. Moving on to the third point of connect, you need to have endpoint management. If I don't have an endpoint management, I have established a way through which all my devices can connect to my platform. I've also ensured that the data is going to be sent from the device to the cloud, and the cloud can send back to the device as well through a secure channel. But if I don't actually identify from which device which data is coming and how this data has to be processed, then it becomes a failure of the system. This is where endpoint management comes into picture. Endpoint management basically helps you in managing the device's endpoint identity, the metadata, and the overall life cycle involved with respect to these things as such. Okay, so to put it quite simply, it basically helps you identify from which device which data is coming and what needs to be done with this data as well. Now, coming on to the next feature is analyze, and the first thing that you need to do for analysis is the stream processing. Now, if the data coming from the device is not on a real-time basis, then my system is of no use. There's no use if I tell my system to switch on the AC at my home, and by the time I reach there, if the AC is not even turned on, then it's a failure on my system. Okay, so real-time analysis of the incoming and outgoing data must be done with respect to different aggregations, filtering, correlations, processing, and so forth. Okay, now apart from this, what you need to do is that this is raw data that is being streamed from all the things. You need to identify which is contextually important information which is going to be taken forward. So once I have the relevant information, then I can even generate composite streams of information which can be taken ahead for future analysis and understanding as well. Now this is what your data enrichment process does. Then you have event store. Now in event store, basically any information that you want can be queried and visualized from the vast amount of data which is present on my cloud platform. Okay, now this in turn can also help me get a better insight and analysis. If I have all the enriched data present on my cloud platform, I have a tool which helps me identify what is needed, helps me analyze this data, helps me visualize it, then definitely it becomes more useful as well. And when I have data coming from different things as such, this in turn can also lead to being a collection of big data. Now, when I talk about big data, it's not just few GB of data, it's going to be terabytes of data. Because the data generated from the things around us is that vast. And if you're doing it over a period of time, then definitely it is going to grow into a big data domain as well. Now, coming to the third feature of Internet of Things comes enterprise connectivity. So this is what I was basically telling you about. Let's say I have a requirement from my retailer or even an enterprise organization which is present. It could be Amazon, it could be Flipkart, anything as such, any enterprise organization which provides me a service. If I can connect to them through this platform, then definitely my overall process also becomes easier as well. Let's say there's a service provider. Okay, let's say there's a leakage in my plumbing, or let's say there's some issue with respect to my electricity. Then it can contact to the corresponding service provider, it can send them a detail, and correspondingly they would be dispatched. This would in turn reduce my effort of having to check the problem, having to call someone, wait for them to come back. All that gets reduced to minimal required effort as well. Now, how does this communication happen? So for that we have REST API. Okay, once I've integrated my REST API with respect to the cloud application and my Internet of Things, then communication between the enterprise, communication between the platform, and the communication between the things around us can be made more efficient and can be more easy as well. Now, the third aspect is command and control. If I don't have command and control on my platform, then it's of no use. Yes, I build a very great environment, I build something that's quite extraordinary, but if I cannot command it, if I cannot control it as per my requirement, then the system in itself is not useful. If I cannot tell my door in a smart home to unlock when I want it, then it becomes failure on my part. If I cannot control the AC on my smart home, then again it's a failure. So always the major aspect when you integrate with respect to these things, the major thing is that you need to ensure there's a huge control on the system and you're able to command it as per your requirement. Now this command could either be through a voice-based recognition, it could also be a message that you can send through your mobile application and so forth as well. Okay, so now let's start with the Raspberry Pi OS installation. I'll help you understand how you can actually install Raspberry Pi operating system once you've bought the Raspberry Pi. Okay, so we'll divide it into different parts. First, let me help you understand the different operating systems that are available at present. Okay, Raspberry Pi in itself supports multiple operating systems as such, but we'll mainly be working on Raspbian. Okay, so these are some of the most popular operating systems supported on Raspberry Pi. So you have RIS OS, you have FreeBSD operating system, you have NetBSD operating system. Plan 9 is again from Bell Labs, as well as Windows has its own Windows 10 of IoT version. Okay, so for this session we're not going to go into the Windows 10, we'll stick to the core Raspberry Pi operating system. Now for downloading the operating system, you can go on to the original site, that is raspberrypi.org, and there in the downloads tab you can download the operating system. Let me just show it to you. Okay, so this is the Raspberry Pi homepage, and here if you go on to the download section, you can download the operating system. Now if you are starting off with Raspberry Pi and Internet of Things, trust me, this is the best place that you can find a lot of information with respect to it. Okay, most people actually publish their details with respect to the projects that they're working. Many popular projects are also available. You can find a lot of help as well as good information here. Okay, so this is definitely the place to go to. If you go on to the download section here, okay, this will either show you two options. You have Noobs or you have Raspbian. I would recommend that you go with Noobs because this is a complete package with respect to the different operating systems as such. So here again you have Noobs and Noobs Lite. So my recommendation would be you download Noobs and make sure you're using a 32 GB memory card. Okay, this would be really helpful because it gives a lot of memory for your operating system. So in case if you're going for a 16 GB or below, I would recommend you go with the Noobs Lite. But make sure you have the bare minimum of 16 GB in case if you're working with Raspberry Pi. But do not mistake me when I say use a 16 GB memory card. You can install it on an 8 GB as well. But again, the operating system has less memory to work with. So at least go for 16 or higher. 32 is what I would recommend. So once you download this zip file, or you can even download it via torrent. Okay, but I would recommend download it as a zip file. Let me show you the file. So this is the Noobs file. Let me extract this. Okay, it may take some time. Okay, it's about a 1.5 GB file. Okay, the Lights version is slightly lower in comparison, but this is something that I would recommend in case if you're working with Raspberry Pi. Okay, so I have my Noobs folder here. So what you need to do is that you need to copy everything inside the Noob folders and then paste it inside the SD card. Okay, make sure you're not directly copy pasting the folder that you have extracted.
ഇത് വൈഫൈ തന്നെ ആംപ് കണക്ട് ചെയ്തിട്ട് ക്ലിക്ക് ചെയ്തിട്ട് വർക്ക് ചെയ്യുന്നതാണ്. ഇത് വൈഫൈയുടെ RGB സ്ട്രിപ്പ്, ഇത് നോർമൽ RGB സ്ട്രിപ്പാണ്. ഇതും RGB മൊബൈൽ ആപ്പ് വൈഫൈ നമ്മളൊന്നും കളർ ചേഞ്ച് എല്ലാം ചെയ്യാൻ പറ്റും. ഇത് വന്നിട്ട് ലൈറ്റ്സ് ലൈറ്റ്സ് ആണ്. ട്രാൻസ്പെറന്റ് ഒരു അത് വളരെ സൈസ് നോക്കിയൊക്കെ എടുത്തത് ഇതാക്കാൻ പറ്റുമോ? അടിപൊളി. മാർച്ചിൽ എഴുതി വെച്ചാൽ പുതിയ പ്രൊഡക്റ്റ് ഒക്കെ ഉണ്ടെങ്കിൽ ഞങ്ങൾ നിങ്ങൾക്ക് അയച്ചു തരും. क्या हो? क्या? പറഞ്ഞ അതിനെ കുറിച്ച് പരിചയപ്പെടുത്ത്. വരുന്നതിനായിട്ട് രജിസ്റ്റർ ചെയ്യാറുണ്ട്. എന്താ
ഓപ്പണാക്കി നോക്കാൻ വേണ്ടി അയക്കുന്നതന്നെ. ഓപ്പണാക്കി നോക്കാൻ വേണ്ടി അയച്ചതാണ്.
ഞാനുണ്ട് ഉത്തരവാദിയാണ്.
കൊടുക്കുന്നതാണ് കാണുന്നത്.
നിന്റെ വേണ്ടതാ നിന്റെ വേണ്ടതാ
ഹലോ ആ ചാർജർ എവിടെയുള്ള ആ അത് എനിക്ക് അതേ തന്നിട്ടുള്ളൂ ആ കാരണം എൻ്റെ കയ്യിൽ കൊണ്ടുതന്നത് ആഴ്സോ അല്ലെങ്കിൽ അംഷാദാ കൊണ്ടുതന്നത് ആഴ്ച മാത്സിൻ്റെ അടുത്ത് വെച്ചാൽ അതല്ലേ ആ ആ ഹാരിസ് റിപ്പയർ
Coming down, we are computing the basic temperature, the humidity and the pressure, and then storing it into a message string. Now comes the place where I need to do my actual implementation. Now if you remember our problem statement, we have to send the pressure, temperature and humidity as a notification on our mobile device. Okay, so for that I'm going to use InstaPush, which is an application through which I can send notifications across my mobile. So my Python application, that is the final application, will communicate to InstaPush, and that will in turn communicate to my mobile application that on which I have configured it. Okay, so